In the last video, I talked about why the laser is useful, why it has these features like very narrow beam, why it can be used in a DVD player, why it can cut metal. And it all boils down to a laser beam having a very coherent beam, very coherent light rays, or a very coherent wave, or we can also think about it as having rays that are very parallel. Right? In terms of wave coherence, means that for example, the waves, different parts of the waves are always in phase, or has the same phase relation. Okay, so in this video, I'm going to explain how it might be possible to achieve such coherence when we know that, for example, using a light bulb, say a filament lamp, different parts of the filament or different parts of the light bulb would give off light independently, so that the resulting wave coming out, different parts of the wave can be quite unrelated and out of phase. So how is it possible for a laser beam to be so coherent? Let's take a look at the atoms. Now, in a laser, there is a part of the laser where this coherent light is produced. Now, in this part of the laser, let's think about the atoms in the laser. Let's say that's the nucleus of one of the atoms in the laser, and we have orbits around the atoms. Right, from what we already understand about the wave properties, we know that it's really the orbits are really not well-defined circles like that, but waves that spread out. But I'll just keep drawing circles in any case, because it's easy to show. So it's kind of schematic, right? I'm just drawing a circle to represent the orbit schematically. It doesn't mean that electrons are actually following this circle. So anyway, there are different orbits of different energies in an atom, and there are a number of electrons around the nucleus. Right. So we have seen in earlier videos, say if you have a hydrogen atom or some other atoms, if an electron falls from a higher to a lower orbit, if that happens, then a photon is emitted. Okay. And an electron might fall from a higher to a lower orbit for a number of reasons. Either because the electrons in the lower orbit gets knocked off by an X-ray, for example, or the electron from the lower orbit is knocked up to a higher orbit by, say, an electron beam colliding with it, or by an external light source, external source of photons shining on the atom. So there are many ways to make this happen. So in any case, if there is room, if there's a space in the lower orbit for the electron to fall down to, it can happen, and then the decrease in energy would be converted to a photon, which is then emitted. So we have a photon. Now, if I imagine that there are many atoms in the laser that can produce such photons, right? If I say draw a few other atoms, then we might imagine that the other atoms could also emit photons. Okay, so it's also possible that they would emit photons, and I might have, say, a photon falling that orbit to that orbit, that orbit to that orbit, that orbit. And it can happen when these atoms are somehow excited, like I said, by light shining on them or by an electron beam hitting it, for example. So when these other atoms, if these other atoms emit a photon, then the photon would come out in all sorts of random directions. Here, there, there. So we might have a situation like in a torchlight bulb, okay, where the light rays just come out at random, and that's not a laser. The light coming out from such a situation is not going to be coherent. The photons are not even going along the same direction. And there's no reason why they should. I mean, one atom will emit a photon independently of the other atom. They don't exactly talk to each other and try to shoot their photons all in the same direction. So how do we make all the photons go in the same direction? We know that in terms of waves, we talk about coherence in terms of being in phase, the different parts of the wave having a fixed phase relation. But in terms of photons, when we talk about coherence, we need the photons to all get emitted in the same direction, right? And that corresponds to light rays, the different rays in the laser beam all going parallel. So how do we make all these photons go in the same direction? That's the first and most important problem in the laser. And this is how it can be done. Now, the idea that this is possible was first proposed by Einstein as a very important ideas, it seems, and later on verified experimentally by other people. So let's look at this atom again. Suppose that there is the electron in the high orbital and there's room in the lower orbits for it to fall down too. Now, the idea is this. That atom, usually it would not immediately fall to the lower level. It might not fall immediately. There's always some time involved. It might just stay there for a short while and then it falls. Or it might take some time to fall down. Now, whatever it is, the idea is that it might remain there for a very short time before it falls. Now, during this time, suppose that there's a photon coming from elsewhere, either from another atom, okay, or from an external light source. A photon that just happens to have exactly the same energy as the difference between these two orbits, or these two levels, HF. In other words, a photon with the right frequency. Now, when this photon hits this atom, it can actually, in a way, help this electron to come down more quickly. Right? This electron might just stay around in orbits and not fall to the lower orbit, even if there is a space in the lower orbit. Or it might stay there for some time before it comes down. But having an external photon coming in of the same frequency would actually encourage this electron to fall immediately when this photon hits it. And this situation, this process is called stimulated emission. So when this external photon hits this atom, this electron would be encouraged to fall to the lower state, and as a result emits a photon of the same energy and frequency, of course. So in other words, that external photon has just stimulated this atom to emit a photon. Now, when this happens, when a stimulated emission happens, the emitted photon would move in exactly the same direction as the incoming, the outside photon that hits it. In terms of wave, in terms of the wave nature of the photons, they would be coherent. The two waves of photons would be in phase. Okay. So when we have stimulated emission, the two photons would be coherent. If we can talk about two particles being coherent. Okay, but in any case, the waves of the two photons would be coherent. Now, if it can happen once, it can happen again. For example, I might have another, atom that just happens to be along the path of these two photons. Okay, so then this photon and that atom might just happen to have an electron in the higher orbits. Okay, so there's some chance involved down here, but there are lots of atoms around in material, whether a gas or solid. So there's a good chance that there would be another atom like that along the way, and when this newly emitted photon, either this stimulated photon or the original photon, come and hit this atom, it would then stimulate the emission of an electron, of a photon, right? Assuming that this atom has an electron in the excited states or in the higher orbit. So then this would fall and give out another photon in the same direction as before. Right, this electron falls to the lower orbit, loses energy and gives out a photon. So each time a photon hits another excited atom along the way, it will stimulate that atom to emit a photon in the same direction. Okay. So if there are lots and lots of these atoms in the excited state, meaning with the electrons at a higher orbits, then the photons would just keep, one photon produces, one external photon stimulates one photon, and then we have two. Then if each of the new photon stimulate another photon, then we have more. And it sort of multiplies, right? You get more and more stimulated photons. So it doubles and doubles and doubles, and then we get lots and lots of photons all going in the same direction. And that's what happens in a laser. It is all this stimulated emission that produce photons that that are all in phase and therefore coherent. Now, in a real laser, of course, there are lots of technical details involved, and I will briefly touch on some of these in this and the coming video. And the first detail that I want to mention, I think before I finish off with this video, is this. Now, this whole idea rests on one assumption, right? You might have already been wondering, how are we going to get all these excited atoms? I mean, atoms are normally, in the ground state, so to speak, meaning that electrons tend to just be at the lowest level. It's like if you let go of a stone, it will just fall down. So all the electrons tends to crowd around the lower orbits, right? So the orbits will all be filled up. Low orbits will all be filled up. So, but as I said, right? Okay, we can try to remove some electrons from the lowest orbit, the inner orbits, so as to allow electrons from higher to fall down. We can do that by either shining strong light at the atoms or hitting them with an electron beam, or just heating it with a high temperature. There are lots of ways that people have found of doing this, or even passing electric current through it, because they do it in semiconductor lasers. Okay, so there are many ways to make the electrons go up or go away from the lower orbits. So that in itself is not the problem, but the practical problem in a laser is that the electrons that have been excited, or atoms that have been excited, the electrons tend to fall back down very quickly. After all, as I said, if you drop a stone, it will fall. The stone is not going to just stay around, hover around in the air for a bit before it falls, right? It's just going to drop right down. And it might just drop right down and emit a photon before the atom has a chance to be hit by an external photon. So it might just give out the photon first, right? It's not right. It might not wait around for a photon to hit it and get stimulated. Why should it? So it might just emit the photon quite quickly, and that's a problem because if the excited atoms emits its photon as soon as it is excited or in a very short time, then there's no chance for external photons to hit it, and therefore no chance for stimulated emission. And even if external photon hits some of these excited atoms at random, there might not be enough excited atoms for stimulated emission to happen. And then we won't be able to create this situation where we have lots and lots of stimulated emission and to get a laser beam. So that's not very helpful. Okay. So it means that the first and most important technical problem that has to be solved in making a laser work is that there must be enough excited atoms. There must be enough atoms with electrons in the excited state. Okay, electrons in the excited state. There must be enough atoms in the excited that remains in the excited state for a long enough time, right? For long enough, so that the external photons, also that doesn't have to be external, can be from atoms inside, so that other photons have a chance to hit and stimulate emission from them. So we need a situation where there are lots and lots of excited atoms and they remain excited for sufficiently long time. Now, when we say sufficiently long time, it usually doesn't mean minutes or hours or days. We're not talking about such a long period. We are probably talking about some fractions of a second, okay, which is usually enough. Maybe even microseconds or less, which is enough because these photons, external to the atom, they're traveling at the speed of light. So they just, if these photons are around, they would just hit the atoms in a very short time. Okay, so but it is necessary that there are many of these atoms that remain excited for sufficiently long time. So there's a description for this situation where say an electron stays up even though there's space for it to fall down, so stays up for a bit of time. Now the word that describes this situation is called metastable states. So we like the electron to somehow remain in a metastable state. Meta as in, why don't we just say stable? Because meta means it's not 100% stable. Okay, it's sort of stable if you don't disturb it, but the moment you have this external photon coming in, it will stimulate the emission. It will just fall right down. Okay. So that's how we would describe the state. And then the situation where we have lots of atoms in an excited state, that situation has a name as well. That situation is called population inversion. Now, population here refers to the population of the atoms of the atoms. When we say inversion, population inversion, right? Let me describe this in a little bit more clearly. The population here refers to the population at each energy level. Like I have often in past videos drawn energy levels, say for the hydrogen atoms. Okay, so there are these energy levels, and we would expect that there are more atoms in the lower levels, right, than in the higher level, because those atoms with electrons in the higher level would tend to go to the electrons there would tend to fall to the lower level. Okay, even if it gets excited by external forces. So tendency is that we would normally have more atoms or electrons that are in the lower level, and we have less in the upper level. That's kind of what we would expect. Like when you drop a stone, it will actually fall down. Now, so population, the word population refers to a population of the atoms that has electrons at each energy levels. Now, population inversion means that the normal population distribution, is to have more electrons in the ground state, fewer electrons in the excited state. Now, population inversion just means that this situation is reversed. Right? In a population inversion, we would have a situation where there are fewer electrons in the ground state and more electrons in the excited states. Okay, so these electrons sort of stay up because it is somehow metastable. But that's what we hope to find. That's what people have been hoping to find anyway. situations where the electrons can be metastable. And over the years, indeed, people have found such materials and situations where they can have metastable states, and that's how lasers have been invented, and that's how we can use it today. So therefore, not only must we have the metastable state, we must produce this situation where we have lots of electrons in this excited, this higher energy metastable state. And this situation with lots of electrons at the higher energy state is called population inversion. So in order to actually be able to make a real laser, it is necessary to solve this technical problem of creating this population inversion inside the materials in the laser.